Okay, this is going to be part 3 of this paper, the Edexcel Physics IGCSE from January 2021, which is also used for the double award. So it's paper 1, and physics has 2 papers, double science only has 1 physics paper. Okay, in the first video we went through questions 1 and 2, so hope you liked it, shared it with your friends, and you subscribe so you know whenever I upload a new video. Questions 3 and 4 were in part 2. They were both on mains electricity and safety features and all the equations that you can see as I scroll through it. Yeah. And then the next part 3 we're going to go through question 5, which is on radioactivity, which is the current topic that I'm teaching on radioactivity, which will not be in our school's mock exam because we haven't finished it, but it will be in this practice paper for those of you who may have already done this to prepare for your mocks. So, a teacher uses a radioactive source which contains atoms of isotope of radium, this isotope radium-226. Give a safety precaution that would reduce the teacher's exposure. Yeah, so that means the total amount of radiation that could be affecting the teacher when working with a radioactive source. Okay, so handle the source with tongs so you never touch it directly, or minimize the time of use, so don't have it out for longer than need be, because both the time and the contact will increase the exposure as well as the proximity to the source. Other things that you need to be aware of, if you check the mark scheme, you'll see alternatives. Make sure that it's never pointing directly towards anyone. So these are closed sources that are used in schools for teachers to demonstrate to their classes. So you always hold them with tongs, always pointing them downwards or towards the Geiger-Müller tube, and making sure that everyone else is a good distance away when they're observing the counter. Okay, so it then continues with the radium-226 that can be represented using the symbol. The symbol for this is given as such. So when you do this, radium-226, you can put in a box. The top number is the total number of protons and neutrons. Yeah, so it's called the mass number at the top, and the bottom number is the number of protons, which is the atomic number of radium. So it's quite a large nucleus. How many neutrons are there? Well, if you take away the 226 from the 88, you will get the number of neutrons. I hope that makes sense. All right, so that's basically how you've got to do it. The difference between two numbers is the number of neutrons, and it's just something you need to know how to do. The teacher then investigates the type of radiation emitted. So remember, there is alpha, beta, and gamma as 3 types of radiation that can come from a radioactive source. Give the name of the piece of apparatus that detects ionizing radiation. So if you're my students, remember I told you can't detect it with your senses. It's ionizing, that means it can be dangerous. So Geiger and Müller, two German scientists, they created what's called the Geiger-Müller tube, also known as the GM tube, and it basically will detect any time a bit of ionizing radiation goes inside it. And if you look up what it's made of, inside the tube there's inert gas. That means a gas from the final group in the periodic table. They don't react chemically, but if some bit of ionizing radiation manages to get in and affects one of the atoms, it will ionize the atom, and the ionized atom will turn into an electron and a positive ion, and that can be detected each time that happens. The electron will go to the anode, the positive ion will go to the cathode, and that can be counted using a counter that's attached to the Geiger-Müller tube. Okay, so that's how it works. The teacher then finds that the radiation emitted from the radioactive source is not detected when the detector is more than 5 centimeters away from the source. state the type of radiation that it must be that is being emitted by the radio source. Well, alpha has the lowest range in air. Alpha can't go through more than a few centimeters of air. So that's how you can work out by its penetrating ability using air, paper, aluminium, and beta is blocked by a thin piece of aluminium. Alpha is blocked by a thin sheet of paper, and of course it can't go through more than a few centimeters of air. So you can work out from its low range in air that it must be alpha. Part D, it says a number of radium atoms, 226, the isotope, decreases over time with a half-life of 1600 years. So, half-life of 1600 years given to you. So the half-life means, let's draw that again, half-life means that it's the average time taken, you should really say, because if you do it each time it might be slightly different. So because it's statistical, it's the average time taken for the number of radioactive atoms or nuclei to decay. Yeah? So it normally happens as a curve, and it will keep on halving every 1600 years. The number of radioactive nuclei will decrease by a factor of 2 every 1600 years, and that's called the half-life. Okay? Some of my students may have researched this, but we haven't done it fully in class, which is why it's difficult for me to add a radioactivity question into the mock exams, because most radioactivity questions will contain a question about the half-life. And you can understand it by just going through this model answer. The radioactive source contains 2.66 times 10 to the 21 atoms of radium-226. Remember, 1 mole of radium would be 10 to the 23 atoms, so we've got about 0.01 moles, or in that order, yeah, about a percentage of a mole. So that you can measure it in atom numbers if you know how to do that. Well, they're giving you the atom numbers. So approximately how many atoms of radium-226 will remain in the source after 800 years? Now remember, the half-life is 1600 years. That means that it will take 1600 years for the number to halve. Okay? So if it takes 1600 years for it to halve, in 800 years, it will be less than half. So if it goes down A, there's too many have decayed. It will be more than 1600 years for it to go to more than half. So the 0.67 is about a quarter, I think, of 2.66. Yeah, so that's more than half, so that would be more than 1600 years. So A, too many have decayed for it to be A. B, exactly half have decayed in B. Yeah, so if half have decayed, it's gone from 2.66 to 1.33. So if it's gone exactly half, it would take 1600 years on average for that to occur. Okay, so that would be the half-life. That means, 1.88 is less than half, and 2.66 is exactly the same as what you start with. That means no time must have passed because none have decayed. So the only answer it can be is C. Okay? So that's how you do a radioactivity question. Hope you found that useful for those of you who finish a topic, and for my students, that will be what we continue with once the mock exam is done. So, question 6. When a rubber ball is dropped, it hits the floor and bounces. So this is about investigation of forces and motion and kinetic energy, if you like, because it starts off with gravitational energy, it changes to kinetic energy, and the question is about designing an investigation. So it's a design and investigation to determine how the temperature of the rubber ball affects the maximum bounce height, if you like, the maximum height the ball reaches after it bounces. Okay, well, the maximum height it reaches when the ball bounces, that will be the what you need to measure, and anything you need to measure after you've changed the temperature will be called the dependent variable. Okay? So the independent variable is the temperature that you set the ball to. So changing the temperature will affect the bounce height. So when you're answering questions like this, you need to know what's the independent variable, the thing that you decide to vary, and then what you need to measure as a result to be able to see the effect it has on the bounce height in this case. And then you need to also think about the variables that need to be controlled. Why is that? Because the variable that needs to be controlled, to make it a valid test or make it a fair test is crucial, that you don't change anything else. So for example, you should keep the initial height, fixed. You're always doing it from the same height. You're just changing the temperature, okay? And then you're measuring the final bounce height. And then, so you need to also think about, well, how are you going to get high quality data? So things like repeating and averaging. Why do you repeat and average? Because you want to get the mean average. Okay, you want to get that. You want to do it more than once to see that you have reliable data, that it wasn't just an anomalous result. And you want to do different heights. You want to do multiple sets of data. You want to do it at different temperatures. You want a good range of temperatures so that you can plot it as a graph. And at GCSE, we always say that you want at least 5 sets of data. And you record and measure the maximum height accurately. How do you do accurate measurements? Well, you get at eye level, to avoid parallax errors, and you fix a ruler where adjacent to where the ball is bouncing, so quite close to it, so you can use your ruler when you're at eye level, and you don't adjust the ruler, so you kind of clamp the ruler, make sure it's vertical. So that's the other thing to ensure that you have accurate data, is making sure that you don't move the ruler. You're basically trying to determine how high up the ruler it bounces, and you may need to obviously do it more than once to make sure that you've recorded it as accurately as possible. Remember, the ball is moving when you're actually trying to record the maximum height, so you've got to think, okay, how are you going to measure it? And do you measure it from the bottom of the ball or the top of the ball? Well, if it hits the ground, the bottom of the ball is where you want to measure it from, because it moves from the ground, the bottom of the ball, and then the best place to measure it again from the ground is the bottom of the ball when it's reached the maximum position. So those are the basically the key points for this exam. And then to get the marks, there's 6 marks. So you've got to think of how clearly you can communicate your understanding. So I always tell my students, it's depth, detail, and clarity that gets you the marks. So the depth is everything that I've talked about, and the detail is written in the notes that I've made for you, and you got to then put it into the space provided. So I'm not doing that for you. You've got to think of, how am I going to verbalize all my understanding of it? So you've got to also then choose a suitable method, and to be able to communicate it. And here it says that you may draw a label diagram. So the label diagram would help you with your wording. So you always say, set up the apparatus as shown in my diagram to start your method. So for example, how are you going to heat the ball? Are you going to use a thermometer? Don't forget that what you measure, you need to say what you're measuring it with. Initial height of ball is is kept constant. That's one of the variable results. That you control variables. So, and also you should ensure that it's not moving when it's dropped. So in other words, it's dropped from a stationary position, each time. So these are the kind of things that the depth, the detail that can get you the marks, okay? And then also don't change the surface that you're bouncing it on. Always make sure you choose the right surface which will get you a good bounce, okay? So that's the kind of the points that you need to make. Everything that I've talked about, you've got to put, and you get 6 points. So you've got to look at the mark scheme and see what they give points for. And remember, you can find this mark scheme on the websites quite easily because it's 2021. All right, I think I covered everything. And let's do one more question. So recently we did magnetism. Very strong magnets can be used using an element called neodymium. Okay. Now I don't really know much about neodymium, but you need to just follow the questions. The diagram shows two magnets, X and Y, drawn excuse me, drawn in the diagram when they are held close together. Okay, so they've put the south pole at the top and they want you to finish the diagram. And it says a uniform magnetic field is produced in the space between the magnets. Diagram 1 shows the south pole of magnet X. Complete the diagram by drawing a uniform magnetic field and labeling the pole of magnet Y. So they've left it off. So how do you do that? You want 3 marks to do this question. So the 3 marks is 1 for labeling this as the north pole. That's magnet Y, because magnet S was the south pole. To get a uniform field, uniform means straight and vertical lines. So I use the ruler to draw straight and vertical lines. So that's one thing, that they're going straight and uniform, and they're equally spaced. Equally spaced for uniform field means a constant magnetic field strength. If you're not drawing them equally spaced, where they are closer is suggesting that the magnetic field is stronger in that position. So that's magnetism, and the second part now is testing you further on this theory. Diagram 2 shows the magnet being used to lift an iron ball. The iron ball is shown at the instant it leaves the surface of the table. So there's a magnetic force upwards. I've drawn the weight downwards. It's coming up later on. Now, if it jumps up and is attracted to the magnets, and actually the magnet is able to lift it, that means the magnetic force upwards, the arrow length must be greater than the weight arrow length downwards for it to be for there to be a resultant force upwards. So this is linking magnetic forces with forces in motion, which is topic 1. And that's what happens in GCSEs. It's not always a question that is linked to one topic alone. Explain why the iron ball experiences an upward magnetic force. Well, it experiences an upward magnetic force because, first of all, iron is a magnetic material. Yeah, so you got to say that iron is a magnetic material, and that gets you 1 mark. So it is attracted to the magnet. Yeah, so if it was made of aluminium, it would not be attracted. Not all materials are magnetic. Iron, cobalt, and nickel are the ones that I teach my students are the elements that are magnetic. And then it says, by the fact that the magnetic field is induced in it, yeah, so basically when something magnetic like iron is inside a magnetic field, it also becomes part of the magnetic field. So a magnetic field is induced in the iron ball, yeah, when it is near the magnet, yeah. So that's basically how it happens, and therefore the top of the iron ball will induce a temporary north pole in it, yeah, and that means the bottom of the magnet would have been a south pole, yeah. So can you see over here is the south pole? So what happens when you induce a magnetic field in the iron, this top of it becomes a north pole, the bottom becomes a south pole, and that's what causes the attraction. So basically all of the iron magnetic properties of the iron, all the atoms will align themselves with the south pole being at the top, and we call those magnetic qualities of the iron domains. So it kind of aligns itself like compasses in a magnetic field. The iron itself is like it's got lots of mini compasses inside it. They will all align to be attracted to the south pole above it. Okay, and that's how you get the 3rd mark, by understanding that there is a magnetic field induced inside the magnetic material. So the iron ball experiences an upward resultant force, as I mentioned to you before with my diagram. So there's a resultant force upwards, yeah? Draw a labeled arrow on diagram 2. Why? To show the weight of the iron ball. In other words, they want to see if you can draw an accurate force diagram, which is what I did. The weight downwards must be less than the magnetic force upwards, because there's a result net force upwards. That means magnetic force minus weight will cause the mass of the iron ball to accelerate. So Newton's second law is taking place in this question. Okay? So state the formula linking weight, mass, and gravitational field. Yeah, gravitational field strength. So that is equal to this equation. And if you do that, that's how you should do it as a word equation. At the instant shown in diagram 2, which was the one we looked at, the resultant force acting on the ball is 124 millinewtons. Don't forget, it's a millinewtons. So you've got to change. You've got to be aware of the fact. And the resultant force is 124 millinewtons, but the magnetic force is actually 165 millinewtons. So if the resultant force is 124 millinewtons, but the magnetic force is actually larger than that, that's because you've got to take into consideration the fact that the weight is acting against the magnetic force, which reduces the 165 millinewtons to, it reduces it to 124. So this is the resultant force, yeah, which is the magnetic force upwards, 165 minus the weight. So because you know the resultant force is 124 millinewtons, and you know the magnetic force is 165, you can work out what the weight must be, the difference between those two forces, which is this line here. And once you can do that, you get the mark. And remember, the units are in millinewtons. Yes, that means 10 to the minus 3 newtons. So once you know it's 10 to the minus 3 newtons, that you have to put it as 41 times 10 to the minus 3 in the equation to be able to divide it by the gravitational field strength, which on Earth is always 10. Remember, this is a G on Earth is always 10, is given to you. So you divide 41 times 10 to the minus 3 by another 10. It becomes 41 times 10 to the minus 4. And that allows you to work out the mass of the iron ball, which if you multiply it by 1,000 would be in grams, but they want it in kilograms. So you could write it either in standard form like I have above, or if you want to just change it, it would be 0.0041 kilograms. And if you get that correct, you will get the 4 ticks I've shown you to get the 4 marks for this question. Hope that makes sense. And then the final part of this question says, explain why the resultant force acting on the iron ball increases as the iron ball moves towards the magnet. Well, obviously, the closer the two objects are to each other, the greater the intensity of the magnetic field. You can't pull the iron ball from a distance which is too great, because the magnetic field strength decreases with distance. So you know that the resultant force, yeah, is equal to the magnetic force minus the weight, yeah, and you know that the weight does not change because it's always in the Earth's gravitational field, and weight is mass times gravity, and the mass of the ball hasn't changed. So the only thing that can change is the magnetic force increases with proximity, yeah, and the field strength, yeah, with proximity, or the field strength increases, the magnetic force or the field strength increases with proximity, so the resultant force increases, yeah? So the resultant force will increase because the weight doesn't change, but the magnetic force gets stronger the closer it is. So it's a proximity that increases the magnetic field strength, yeah? The gravitational field strength remains the same. So if you can try to explain all of that, you will get the 2 marks. I hope that makes sense. And I hope you found this video useful. I'm going to take another break. And there's 3 more questions done from this paper. And don't forget to like and share the video with your friends. Spread the word. Support my channel. And make sure you subscribe so you know when the next video is uploaded. Bye for now. Hopefully see you in the next video.